Good morning. Today we are going to discuss the working principle of a steam power plant, the basic components in a steam power plant, their functions, and the basic cycle called Rankine cycle, and one of the performance enhancement method called regeneration. In a vapor power cycle, the phase of working substance changes alternatively. The change of phase allows more energy to be stored in working substance that can be stored by only sensible heating. The working substance expands as a vapor, but it is compressed as a liquid with much smaller specific volume. Thus, a very little expansion work is used for compression process. The common working substance is water. From the water, the vapor is utilized for this cycle. So the plant and the cycle is called as steam power cycle and steam power plant, even though water is used in the liquid phase during the part of a cycle. A steam power plant majorly consisting of main components like a turbine in which the high pressure steam is supplied from the boiler, which is getting expanded and converted into shaft work in the electrical generator, where it is going to utilize very useful work. The low pressure steam coming from the turbine will be entered into the condenser, where it will get changes its phase by converting into a condensate due to mutual exchange of heat from the water supplied from the cooling tower, where it will absorb the heat and it will get warm, and then it will be supplied to the cooling tower. The condensate coming from the condenser is again enters into the pump, where it will be supplied to the boiler. In the boiler, the combustion process will be taking place, duly taking the fuel and air supply, and with this heat supply, the water is getting evaporated and high pressure steam is generated, and it will be supplied to the turbine. After the combustion, the combustible gases is going to through the chimney in this manner. So this completes the cycle. So we can conclude that the steam power plant consists of major components like boiler with its mountings and accessories, turbine, condenser, feed water pump, electrical generator, cooling water tower, chimney, circulating water pumps, etc. The four basic components of vapor power plant shown in the figure. Each component in the cycle is regarded as a control volume operating at steady state. Initially, the boiler, where the feed water is received from the pump and heat will be supplied, it will get heated up to saturation, that is 100 degrees centigrade. After that, at constant pressure, the again heat addition will be happen. The high pressure steam is generated and it will be supplied to the turbine. In the case of turbine, the vapor leaving the boiler enters the turbine, where it expands isentropically to the condenser pressure. The work produced by the turbine is a rotary, that is shaft work, and is used to drive the electrical generator or machine. Again, the low pressure steam entering into the condenser. The condenser is attached at the exit of the turbine. The vapor leaving the turbine is wet vapor, and it is condensed completely in the condenser by giving its latent heat to some other cooling fluids like water. The condensate will be supplied to the pump, where the liquid condensate leaving the condenser is pumped to the operating pressure of the boiler. The pump operation is considered as isentropic compression. Now we can see this basic Rankine cycle and the process involved in the cycle in order to assess the efficiency of a steam power plant. Here we can see the TS diagram, where we can explain that the process 1 to 2 is the constant pressure heat transfer in the boiler. From if here there are 2 points, that is 2, if the saturated steam is leaving from the boiler, then we can represent 2 point on the saturation line. If superheated steam is leaving from the boiler, then we can signify the point as 2 dash. In this case, we are assuming that the saturated steam is coming from the boiler in order to evaluate the efficiency of the cycle. The process 2 to 3 is a reversible adiabatic expansion in the turbine. Process 3 to 4 is a constant pressure transfer heat transfer in the condenser. The reversible 4 to 5 is the process called reversible adiabatic compression process, that is in case of feed pump 4 to 5. Usually the pump work required is in order to drive the pump, the work required is very little. That is, hence usually we used to ignore the pump work when compared to the output of the turbine. Then again 4 to 1, if pump work is ignored, the heat supplied to the water up to 100 degrees centigrade. We know that the efficiency of a cycle is ratio of work done to heat supplied. Work done is nothing but heat supplied minus heat rejected. In this cycle, the heat is being supplied in two phases, that is from 4 to 1 and 1 to 2. Hence, here we are writing that the heat is supplied from process 1 to 2 and process 4 to 1. Say for example from process 1 to 2, here we can observe in the figure, that is 1 to 2, here the water is at 100 degrees centigrade and here the water is under saturated vapor state. So we are writing that H2 minus, that is fluid state, HF1. Using basic principle, we can simplify that H2 as HF2 plus X2 into HFG minus HF1. By the assumption already we have considered that at point 2 the steam is under dry saturated steam. So obviously the dryness fraction at that particular junction is equal to 1. Hence the heat supplied between 1 to 2 we can write it as HF2 plus HFG2 minus HF1. We know that at constant pressure, that is P1 is equal to P2, because the heat supply is being takes place at constant pressure. The magnitudes of fluid enthalpies at particular pressure will be equal. So HF1 is equal to HF2. Ultimately, we can say that the heat supplied between 1 to 2 is HFG2. Similarly, again we will move to heat supplied from 4 to 1. If we are ignoring the pump work, then we are using, because ideally speaking the pump work is very less, that's why we are ignoring. So it will be 1 to 2 process, that is 4 to 1 process, the heat supplied is that nothing but HF1 minus HF4. And we can say that at constant pressure P1 is equal to P2, HF1 is equal to HF2, P3 is equal to P4, HF4 is equal to HF3. So total heat supplied from 1 and 2 equations, we can say that it is HFG2 plus HF2 minus HF3, which is ultimately this is HF2 plus HFG2 is nothing but H2, that is absolute specific enthalpy, that is absolute enthalpy at point 2, and HF3 is the fluid enthalpy at point 3. Now we can move to heat rejected between 3 to 4, which is nothing but between 3 to 4 is condenser entry and condenser exit. That is here at point 3 the steam is, that is the fluid is under vapor state, and at point 4 the fluid is under liquid state. So the heat rejected between 3 to 4 we can represent as H3 minus HF4. Similar simplification as discussed earlier, that is HF3 plus X3 into HFG3, that is the fluid enthalpy is HF4. Here we can notice that at point 3 there will be a wet vapor, obviously the value of X3 will be existing. Whereas at point 2 we have assumed that the steam leaving the boiler is under dry saturated state, whereas after expansion from the turbine the steam is under wet condition. Similarly, we can simplify this. Finally, its magnitude is X3 into HFG3. Here we can simplify that work done is nothing but heat supplied minus heat rejected, and the magnitude after simplification we are going to get that it is H2 minus H3. So efficiency of a Rankine cycle is work done by heat supplied, that is H2 minus H3 by H2 minus HF3. In a simple Rankine cycle, a significant amount of heat is added for sensible heating of a compressed liquid coming out of the pump. The mean temperature at which the sensible heat is added is much lower than the source temperature. Thus, the efficiency of Rankine cycle is much lower than that of the Carnot vapor cycle, which is the ideal cycle. In order to improve the efficiency of a Rankine cycle, there are many methods, out of which now we are going to discuss one method called regeneration. The efficiency of a Rankine cycle can be improved by heating the feed water regeneratively. The main principle behind the regeneration process is the reduction in heat supplied when compared to ideal Rankine cycle. The mean temperature of heat addition in the Rankine cycle can be improved by increasing the heat supplied at high temperature, such as increasing superheat, increasing boiler pressure and using reheat. The mean temperature of heat addition can also be increased by decreasing the amount of heat supplied at lower temperature. Here we can see the regeneration cycle layout where the steam coming from the boiler will be entered into the superheater, and again from the superheated steam will enter into the turbine where the shaft work will be converted, and in the turbine during the expansion, that is at point 2 and point 3 at two places, now we are leaking the steam. That is called as bleeding of steam. Bleeding of steam will be taking place at 2 points if we are going to use the two feed heaters. The number of feed heaters will be limited based upon the capacity of the steam power plant. If the steam power plant is a smaller one, then maybe one feed heater may be sufficient. If it is depending upon the capacity, the number of feed heaters will be increases. In this case, we are going to consider there are two feed heaters. After certain expansion at point 2, the bleeded steam will be entered to the high pressure heater. Because why we are calling this feed heater as high pressure feed heater? Because the steam we are receiving is at a little bit high pressure when compared to point 3, and this is called as low pressure feed heater. At the point 3, again after certain expansion we are leaking certain amount of steam and it will be supplied to the lower pressure heater. Say for example, here the steam is supplying 1 kg, then after certain expansion at point 2 we are bleeding a steam of mass m1 kg. The leftover steam called 1 minus m1 kg will be supplied to the next expansion process. And after certain expansion at point 3, again we are bleeding the steam amount, say about m2 kg. The leftover steam, that is 1 minus m1 minus m2 kg of steam, will be supplied to the condenser. Where in the condenser already we have discussed that the mutual exchange of heat will takes place, and the low pressure steam, that is of 1 minus m1 minus m2 kg, will be converted into liquid condensate, and it will be supplied through the pump to a feed heater. That is 1 minus m1 minus m2 kg of low pressure steam will be converted into liquid state and it will be supplied to the low pressure heater, where the steam of m2 kg will be supplied here, and mutual exchange of energies will take place. That is, the steam loses the energy, whereas the feed water, that is liquid, will gain the energy and it will be supplied to the next feed heater. The steam, low pressure steam, which is losing the heat, and it will be converted into liquid state, and again it will be supplied to the main line. Again, the feed heater, from high pressure feed heater, the amount of steam coming from the low pressure heater is about 1 minus m1 kg. Again, m1 kg of steam will comes here and mutual energy will exchange will takes place. Again, it will be condenses and m1 kg will be supplied to the main line. Similarly, from here, again, ideally speaking, 1 kg of steam here we have supplied, and again 1 kg of steam and the feed water after condensation we are supplying to the boiler using a feed pump. This completes the regeneration cycle. The main intention behind the regeneration cycle is we are going to use the energy from the low pressure steam, and we are supplying that energy instead of supplying external source. We are supplying the same energy to heat the feed water, so that the amount of heat supplied to the boiler will be reduces. Obviously, the efficiency of the cycle will be increases. Here we can see the thermodynamic analysis. Here, say for example, this is one point is entry to the turbine. After certain expansion at point 2, m1 kg will be supplied to the feed heater, that is 0.7, as we have discussed earlier. And again after certain expansion at point 3, some steam is being bled, and it will be supplied at point 6, and remaining steam, that is 1 minus m1 kg, will be supplied to the condenser, where it will be converted into the condensate and it will be supplied to the feed heaters simultaneously. Thus the cycle completes.